Welcome to the explainer. Have you ever really stopped to think about it? How does a simple thought, like, I want to pick up that cup of coffee, turn into an actual physical action? Well, it's this incredible biological journey, a story of amazing speed and precision. And today, we're going to follow that signal from the spark in your brain all the way down to your fingertips. Okay, so let's just dive right into that question. On the surface, it seems simple enough, right? But the process underneath is this fascinating cascade of electrical signals, chemical reactions, and mechanical force. So let's do this. We're going to follow a single command from your brain all the way down to the microscopic engines that are humming away inside your muscle fibers. So everything, and I mean everything, kicks off with a decision. Your brain takes that choice and translates it into a command, this powerful electrical impulse called an action potential. And it fires from a super specialized nerve cell, a motor neuron. And this is not some lazy little current either. Think of it more like a high-speed message, a shockwave of pure electrical energy just racing down the neuron's long tail, the axon. It's got one destination and one destination only: the specific muscle it needs to wake up. All right, now we get to a really critical handoff point. See, the nerve doesn't actually touch the muscle. There's this tiny, tiny gap between them. And to get across that gap, the signal has to pull off this really cool trick. It's got to switch from being electrical to being chemical. This special connection point is called the neuromuscular junction. You can almost think of it like a highly secure checkpoint. It's right here that the electrical signal from the nerve is going to release a set of chemical keys, and those keys are what will unlock the muscle on the other side. So here's how that chemical handshake actually goes down. The electrical wave arrives and boom, it triggers the release of these chemical messengers called acetylcholine. These little guys just flood the gap and they lock onto receptors on the muscle's surface. That action throws open new channels and it creates a second electrical wave that now spreads across the muscle and dives deep inside through this whole network of tiny tunnels. Okay, so once that electrical signal has made its way inside the muscle fiber, it triggers the release of the real star of the show. Stored away inside this special network called the sarcoplasmic reticulum is the one ingredient you absolutely need for a muscle to contract. And that key ingredient? It's calcium. The electrical signal basically throws open the floodgates of this storage network, unleashing this massive burst of calcium ions that just wash over the entire muscle cell. This calcium flood, that's the master switch. That's the final go signal that turns the muscle's engine on. So, how in the world does a burst of calcium set off these tiny but incredibly powerful engines inside the muscle? Well, for that, we have to zoom way in to the most basic unit of contraction, a little thing called the sarcomere. Now, inside every single one of these sarcomeres, you've got two main protein filaments. You have these thin ropes called actin, and you have these thick motors called myosin. But here's the catch. The myosin motors can't just grab onto the actin rope whenever they feel like it. No way. They're blocked by a pair of protein safety guards, troponin and tropomyosin. But when that calcium floods in, it binds to these guards, makes them change shape, and forces them to move out of the way, finally exposing the spots on the actin rope that the myosin wants to grab. And with those sites now open for business, the myosin motors just spring into action. They reach up and attach to the actin, they pivot with some serious force, that's the power stroke, and they pull the actin rope inward. Then, using a little bit of energy from a molecule called ATP, they let go, snap back, and grab on again a little further down the rope. This whole cycle, attach, pivot, detach, reset, it happens thousands of times a second across countless myosin heads, all working together like a perfectly synchronized rowing team. And the result of that molecular tug-of-war is pretty obvious. On the left, you see the relaxed sarcomere. It's long, it's stretched out. But on the right, after that power stroke, you can see the myosin has literally pulled the actin filaments inward, physically shortening the whole unit. It's gotten smaller. And this, right here, this is the whole point. This is the big reveal. When millions and millions of these microscopic sarcomeres all shorten at the exact same time, the entire muscle contracts. That is where the physical force comes from. The force you use to walk, to talk, and, to lift your cup of coffee. Okay, but think about it. A muscle that can't turn off is just as useless as one that can't turn on. So once the job is done, how does this incredibly complex system reset itself so efficiently, just waiting for the next command? Well, the reset is basically the whole contraction process just thrown into reverse. And it all starts with getting rid of that calcium. the cell works really hard to pump all those calcium ions back into storage in the sarcoplasmic reticulum. Once the calcium is gone, the safety guards slide right back into place, blocking the actin ropes again. The myosin motors can't bind anymore, and the whole sarcomere just slides back to its original resting length. And this reset mechanism is just incredibly efficient. The second that go signal, the calcium, is cleared away, the entire muscle machine automatically stands down. This makes sure your muscles are instantly ready for the very next command from your brain, with literally no delay. What is just truly mind-blowing, though, is the speed of all this. This whole complex cascade, from a thought in your brain to a chemical message to actual physical force, it all happens in just a handful of milliseconds. It is literally over and done faster than you can blink. I mean, it is just a stunning testament to biological precision, right? A perfectly coordinated dance of electricity, chemistry, and physics. And the whole thing relies on every single step happening perfectly, every time. Which kind of leaves us with a final thought. What happens when any part of this elegant system breaks down? And what does it really take to keep this incredible biological machine running smoothly day in and day out?